This next stop is still in the western Piedmont, very close to where we were before at Todier Creek, just a little southeast of there. We're going to call it stop 1A, and this is where a big Diabase dike crosses the James River.
We're talking about these rocks called Diabase, and they typically form these rounded boulders like this, completely unlike the rocks at Todier Creek Reservoir. Remember, we talked about the foliation in those rocks. Well, Diabase has absolutely no foliation to it whatsoever. It's just a uniform, dark gray, igneous rock, and it weathers into these round shapes because it has literally no internal structure. It's just uniform crystallized grains of several different minerals, plagioclase feldspar, pyroxene, which is a mafic mineral, and maybe some other minerals like olivine. But one of the things that Diabase always has, one mineral that Diabase always contains, is the mineral magnetite. Magnetite is an iron oxide that occurs in mafic rocks, and one of the ways we detect magnetite is we use these little pencil magnets that balance on this little hinge. And if you hold it up to a rock that contains a lot of magnetite, I haven't tried this yet on this rock, but I guarantee it's going to work. You just approach the rock like this, and bam, look at that. The magnet sticks to the rock. That indicates there's quite a bit of magnetite in these rocks. And there's so much magnetite in these rocks that it's even detectable by sensitive instruments called magnetometers from airplanes. And one of the ways we map these Diabase dikes in Virginia is by using airborne magnetic data. And I'll show you a figure pretty soon where you can actually see the path of the Diabase dikes from the aerial magnetic signature.
So I just downloaded this aeromagnetic map of Virginia from the U.S. Geological Survey website. And it's a pretty interesting map. This is the magnetic susceptibility of the rocks as measured from airborne instruments, with low susceptibility shown in blue and the highest shown in these red and pink colors. You can see, if you know your provinces, the Valley and Ridge province, where we have thick crust and the basement is quite deep, you have these low magnetic susceptibilities. And then in the Blue Ridge province, where the basement rocks, the deeper rocks, have been lifted up high, we have fairly high susceptibilities. But the western Piedmont especially has some quite high susceptibilities. But if you look closely, look at all these stripes that cut across the Piedmont, these north-south or northwest trending stripes. These are all Diabase dikes. So these are all these vertical bodies, vertical sort of planar tabular bodies of high magnetite content mafic igneous rocks, and they have such strong magnetite content that they show up even from airborne instruments.
These are tabular bodies of igneous rock that came up through fractures during the opening of the Atlantic about 200 million years ago. So it's part of what we call the Mesozoic rifting event. Much, much later than the Appalachian Mountain Building or the Blue Ridge Mountain Building. But these rocks are indicative of tectonic events that have affected the Piedmont. Another thing about Diabase dikes is that they are almost always, when you find the boulders, they almost always form a north-northwest to south-southeast line on the ground. And here I am looking south-southeast down this gully, and you can see that this gully, well, probably some farmer put these here, but I bet he didn't move them very far. This gully, the southeastward pointing gully, is just full of these Diabase boulders, and this is typical of how we find them on the landscape, is in these linear patterns running from south-southeast to north-northwest. Another feature of Diabase boulders is this distinctive orange rind. They almost always have this orange rind, and this is because of the oxidation of various iron-bearing minerals and the weathering of those iron-bearing minerals in the ground, in the soil, and it forms this beautiful rusty orange rind.